Hey, everybody. My name is Ash, and we're about to talk about an exciting topic which covers close to a decade of my work. It's titled Internet Scale Search for Semantic, Structural, and Text Information in Real Time, which I guess might be too ambitious for a short conversation, but will at least cover several important issues that exist in most of modern software. They are very well visible when you dive into search, but they also apply to other domains. So when we think about search, most developers immediately remember several brands like Mealy Search, Algolia, TypeSense, and Elasticsearch, all of which kind of have the same purpose: to provide an indexing data structure, generally wrapped into a web server, for you to be able to navigate a fairly large data set. Some of those brands are faster than others. So walking through their website, you may find statements like brand X is consistently outperforming brand Y by a factor of 12 to 200. And it's likely not an exaggeration. So there is a huge spread in the quality of those implementations. But I'm here to say and share some thoughts on like how much faster this can become compared to the fastest solutions on the market. So until maybe last year, most people didn't really think about semantic search. Most of the search around was lexicographic, meaning it's navigating textual data sets. Those pipelines are fairly simple. We take a textual input. Then we use a special algorithm, generally called a stemmer, that would not just tokenize the words with white spaces, but also find the base form of every word. The purpose of this is to produce a fairly consistent set of token identifiers that are later pushed into some inverted index data structure. So most of the search algorithms and search solutions that existed until the last couple of years were designed around inverted indices. That's a very practical and simple data structure. It's just a list for every token that says in which document this token appears. But then in the last couple of years, with new releases and AI-based approaches in search, people started using the term semantic search, which essentially means searching by meaning, not by specific tokens. And the pipeline there is also fairly simple. You take an AI model that produces embeddings. Embeddings are high-dimensional vector representations. And then you use a separate indexing data structure that is rarely an inverted index to navigate those large data sets of vectors. So the closer two vectors of two documents are, the more likely the documents are to be similar. All of this is like a fairly simple pipeline, but most solutions that exist on the market have common red flags. For me, those are things like gRPC, which is Google's remote procedure call library, memory mapping to work with external memory and input-output operations, AVX as the only kind of single instruction, multiple data instructions used by the solution. And this is a frequent topic of debate, but the language in which the system is implemented is also oftentimes a good indicator of how fast the system can go. So most of the time, when systems implemented in C and C++ are not efficient enough, so to really squeeze everything out of the hardware, you generally need to go down to assembly. If your system is not written in one of those languages, chances are that you're leaving a lot of performance on the table. For me, the best example of how much performance you might be leaving on a table is a comparison between a library a lot of C++ developers use anyway, which is the standard templates library's regular expressions implementation. Assuming it's C++, a performance-oriented language, the assumption may be that the solution must be very fast. But in reality, when you match a pattern against a string, you may end up with a performance that is close to 50 megabytes per second. So you have a query that is a regular expression, and you only go through 50 megabytes of haystack text per second. When you compare it to really optimized solutions like Intel's Hyperscan, those can squeeze 10 gigabytes per second on each core. So there is a huge spread even within a single ecosystem such as C++. Generally, when we talk about search, the reference number to remember is that the memory throughput of a single CPU core in most modern systems is 10 gigabytes per second, maybe a multiple of 2 of that. So maybe 5 to 20 gigabytes per second. Most search operations in semantic search, for example, are fairly lightweight. So if you implement them efficiently, you end up being memory bound. So if you're looking into a commercial solution or product that advertises high throughput search through a million vectors, maybe the question you should ask yourself is like how fast the brute force solution would be. Because chances are, even without like a custom product, you can fit within 100 milliseconds within a single CPU core. This point is not just about search. One of my favorite blog posts is by Dan Liu from a few years ago, and he compared the input latency of several computers, and some of those computers were released as far as 20, 30 years ago. So the latency of the response, keyboard response in his case, was actually better on older systems. And there are many reasons for this. So just let this sink in. We buy new devices every year, phones that cost thousands of dollars, yet the input frequency or the input latency on those devices is actually lower than on devices 30 years ago. One of the reasons for this is just physics, but part of the reason is also incentives in our industry. So about 20 years ago, we reached a point when CPU frequency is not really scaling anymore. So we started growing chips horizontally instead of vertically. Instead of increasing the frequencies, we started manufacturing chips with more cores. So whenever we have a workload that is big enough, we split it between multiple cores. That's what hardware designers were doing. In parallel, software was becoming more and more complex, so we started adding abstraction layers. And sadly, we've over-incentivized those abstraction layers, so most of them are kind of useless. None of them are free, so you always pay for those abstractions, and oftentimes you pay with runtime performance. But the other way we pay for those abstractions is once you build up a system in a specific way, time passes, we have new chips a couple of years down the road, and then it's very hard to topple those abstractions and adjust them for new, somewhat different hardware. So we start collecting those legacy solutions, we collect technical debt, and it's really hard to fix. And maybe the last part about incentives is the consumers and the management in our companies. Every day, developers face this request for new features. Well, there's still an endless list of bugs that have to be solved. So we jump to those shiny features without actually taking care of the quality of the software that we write. That's also true for search. Luckily for search industry, in the last couple of years, because we had a wave of incoming developers and interest in new solutions, and also a fair amount of new hardware, we started implementing search pipelines from scratch. And it's not just inverted indices. Actually, all the algorithms and data structures listed on this page are related to search, and none of them are inverted indices. I guess the oldest kind of indexing data structures mentioned here are the space filling curves. Few people would describe them as search data structures, but sometimes they're used in databases like Postgres for geospatial analysis or indexing low-dimensional vectors, especially integers. Another family is k-dimensional trees. They were popular in the 80s and 90s and are still somewhat popular in game engines, Their variations would be octatrees for 2D, 3D. Octatrees would be for 3D cases, and there are also variations for 2D vectors that allow you to search efficiently in low-dimensional spaces. K-dimensional trees don't work very well most of the time for high-dimensional representations. There, the choice is typically locality-sensitive hashing, which is an approach of training a family or like choosing a family of hash functions that would split your vectors into several buckets. Or the approach that I prefer, navigable small-world graphs. It's a graph-like indexing data structure, and it differs from others in various ways. Generally, you compare those structures in terms of their time complexity, space complexity, simplicity of implementation. But to avoid diving too deep into math, sometimes a picture is worth 1,000 words. I guess that's precisely the case here. So the Towards Data Science blog on Medium has this beautiful visualization cited by many companies describing how HNSW actually works. So you build up an index, which is a graph of nearby points. You have multiple graphs of different granularity so that every successive layer contains fewer and fewer points. So at the very top layer, we have just one point, which is the entry point. And we traverse each graph one after another, starting from the top and going to the bottom until we find a dense region close to our query. Despite its simplicity, even such data structures are not easy to implement efficiently. There are at least two very popular implementations, HNSW-lib and Phase by Meta, that are quite popular and have different kinds of optimizations, but they still suffer from things such as excessive memory allocations. So on the hot path, every time you perform a search on a specific layer, those functions would allocate a new priority queue. Those priority queues are not implemented efficiently themselves, but also every time we have to create one, it will be a dynamic memory allocation, which is a non-deterministic operation in terms of its latency, as may result with a system call with your application requesting more pages from the operating system. It gets worse in a concurrent case because not only we deal with a memory allocator that is generally behind a very large mutex in the internals of the C standard library, but also you need to synchronize the access to different nodes of the graph. In that case, HNSW-lib uses a vector or like array of standard template libraries mutexes. All of those are very heavy data structures. And in case of Phase, the logic of those mutexes and logs is actually delegated to OpenMP. OpenMP is a very good starting point for those kinds of optimizations, but it might not be as efficient as handwritten logs for every case. And then maybe the most obvious of optimizations that is lacking in most of those libraries is efficient use of SIMD. So SIMD stands for single instruction, multiple data. It's a family of instruction set extensions that's been added to both x86 and ARM in multiple generations over the last 20 years. Those instructions are not very well understood by the compiler. So in other words, when your compiler looks at the high-level code in C++ or C, it's very hard to map this code into low-level assembly instructions that would allow the processor to handle multiple scalar values at once. The difference in using those kinds of instructions and implementing them in implementing those kernels in assembly, even on the simplest data parallel applications, like computing the distance between two vectors, can lead to 200x performance difference. So a good example for this can be computing dot products or computing cosine distances, the most common metric in any search pipeline these days, for float 16, float 32, brain float 16, or int 8 representations. For these purposes, I wrote a library called SimSimd, And on this slide, I compare it to SciPy, NumPy, and on our website, you can find more comparisons with other libraries. So unlike NumPy, SimSim doesn't really depend on the underlying BLAS implementation. It's a replacement for some parts of BLAS in many ways. Diving deeper, you may ask yourself, like, if you have so many kernels for different kinds of vector representations, what would be the representations to start with? And it's not even just about internet scale search. This year, we saw shift across the industry towards BrainFloat 16. So the hardware support is significant enough for most software vendors to consider BrainFloat 16 as the default form factor, default vector representation, as opposed to Float 32. That's a somewhat weird format. It's not analogous to the IEEE Float 16 representation. It has 3 more bits for the exponent, sacrificing 3 bits in Mantissa, but it's much easier to convert to and from Float 32, and it's also broadly supported on CPUs. Generally, in large-scale search pipelines, that's what people prefer over complicated conversions to int or bits. When working with this kind of BrainFloat representations, you deal with multi-step pipelines, and even when you compute the cosine distance, which is practically 3 dot products with a subsequent normalization step, your inputs are in BrainFloat 16, your accumulation and multiplication happens in Float 32, but then at the end, when you need to compute the norms of the vectors and take the square roots, actually not just the square roots, but their reciprocals, it's better to upcast again towards Float 64. And then the real problems begin. Because if you're implementing all of this in assembly, you'll quickly realize that even though AVX2 supports single precision reciprocal square root approximations in hardware, it doesn't support double precision. In AVX 512, double precision is defined, but in reality, it's only 6 times more accurate than single precision. So we have 32 more bits, but the precision is only 6 times higher. And on ARM, it's not just the fact that the latencies are not defined, but also even the accuracy of the instruction is not defined. So most of the engineering that you will be doing is actually reverse engineering the nature of those instructions. And once you realize that in some cases they aren't accurate enough, you are complementing the reciprocal approximations with something called Newton-Raphson iterations. And you can read more about this in the SimSim repository. That one brings 200 kernels with dynamic dispatch that are currently powering some of the largest databases and search engines in the world. But just one library is not enough to solve search. So we started building up a portfolio of tools that can help developers build up great solutions for tomorrow. And one case where things get even more complicated is text and string processing. Strings is a very good example of non-data parallel workloads, meaning unlike vectors where when you deal with 2 vectors and you compute their the distance between them, the number of scalar values in 2 vectors is identical unless those are sparse representations. In text processing, no matter what kind of algorithm you're using, is it exact search, multi-pattern search, or rolling hashes for fuzzy matching, most of the time your time complexity is super linear. So it's not just, it's taking more time with every new character edit, and the function of complexity is not linear function of the input size. They also oftentimes require some extra memory. Most of the text that you're processing is not aligned to cache boundaries. So a typical cache line size is 64 bytes, and not every character address is a multiple of 64. It may not be a big problem for most search pipelines, but for internet scale, it matters. A more obvious thing would be things such as pointer chasing. So different parts of text or different parts of your matching trie would be located in different parts of memory, would require your CPU to actually jump to different addresses, which is really slow and maybe like 300 times more expensive than computing something on the CPU itself. And the last but not the least, because texts have different sizes, your logic for handling very short strings and very long strings is very different. So In libraries that we implement like Stringzilla and similarly in glibc, the algorithms for strings that are, let's say, a few megabytes in size and just a few bytes in size would use different kinds of loads and stores, sometimes avoiding CPU caches. Just to make this a little bit more fun, this is an example of what this kind of code may look like. So this is not even SIMD, this is SWAR, SIMD within a register, showing you a real code example from Stringzilla on how to emulate SIMD-like behavior with 64-bit words, processing 8-bit characters, 8 characters at a time. So it's very unconventional. It would use bit magic, a lot of shifts, and a lot of trickery. But the library is quite well documented, and not just the code itself, but also the README file with 64 kilobytes of text on how those algorithms work. And the cool part is that SWAR is very portable. Once you implement it, you can also run it on the GPU. So definitely recommend it. With this, we couldn't really stop, and we started assembling more and more libraries. All of them are Apache 2 licensed, free for commercial use. And we use them ourselves for building really large search pipelines and help database vendors to build up better products. We definitely recommend everyone to just benchmark before you buy into any ecosystem. Sometimes we notice that commercial solutions may be 1,000 times less cost efficient than just renting an AWS server or bare metal machine and running an open source library, especially if those libraries provide a lot more functionality and a lot more interfaces and better documentation than the commercial analog. Our libraries don't stop here. And at the start, I mentioned gRPC, networking stacks, I/O. So we continue building out towards those mediums and external memory. All of this is in active development, but also deployed on over 100 million devices worldwide, powering some of the largest databases. So we would be really excited to see more developers joining the ecosystem, and we're happy to see contributors actually learning with us how to use CPUs efficiently. Thank you.